Hello students, I would like to lead us through an example of an oxidation reduction or redox titration. Reading the problem, the quantity of antimony in a sample can be determined by an oxidation reduction titration with an oxidizing agent. A 9.62 gram sample of stibnite, an ore of antimony, is dissolved in a hot concentrated hydrochloric acid solution and passed over a reducing agent so that all of the antimony is in the form of antimony 3+. The antimony 3+ is completely oxidized to antimony 5+ by 43.70 mils of a 0.1250 molar potassium bromide solution. Calculate the amount of antimony in the sample and its percentage in the ore. In the titration, BrO3- is reduced to Br-. All right, so the first thing we need is our oxidation reduction balanced reaction. So we're told that we are converting antimony. Now remember, that would be the charge, but we can go ahead and change that to an oxidation state. And for clarity, I'm just going to remove the phase symbols just until I get my entire reaction to antimony +5. And then the BrO3- ion is converted to the Br-. So balancing, one antimony, one antimony. We do not have to worry about oxygen or hydrogen. Now, we're told it was dissolved in a hydrochloric acid solution. So that tells us this is an acidic environment if I need to balance with hydrogen ion. To balance charge, I need to add 2 electrons so that we're +3 on this side to equal out the +3 on the reactant side. Next, 1 bromine, 1 bromine, 3 oxygen, so I will add 3 waters. To balance hydrogen, I will add 6 hydrogen ions. I have a -1 on this side. I have a +5 on this side. So, -1, +5, I need to add 6 total electrons to this side to get this to also be -1. To get my total number of electrons given and taken the same, I need to multiply through by a coefficient of 3 for that reaction. So my balanced equation will be 3 antimony plus 3 plus, and I know my electrons will cancel, 6 hydrogen ion plus 1 BrO3- yields 3 Sb plus 5, my electrons will cancel, plus 1 Br- plus 3 H2O. Now attaching phase symbols. And I realize I only am looking at my species that are involved in the chemical change, not any of my spectator ions. All right, so the question is, what is the amount of antimony in the sample and the percentage in the ore? So I need to find the amount. Now this ion came from the conversion of the antimony in the ore, which I would assume is a solid. So I'm going to be after my grams of antimony. And I was told that the titration required 43.70 milliliters of the 0.1250 molar potassium BrO3 solution. All right, so starting with either of these, why don't I start with my molarity? And so I have 0.120 mole per liter of my KBrO3, and my reaction requires 0.04370 liters of the potassium BrO3 solution. And this, of course, is liters of the potassium BrO3 solution. So that'll cancel that. Now, my reaction involves the BrO3 ion. I'm now in moles of KBrO3. So, just to be in terms of my actual reactant, for every 1 mole of the KBrO3, it's 1 mole of the BrO3 ion. Okay, just to condense this to give myself plenty of room. All right, now I'm to what I got from my balancing. For every 1 mole of the BrO3-, I have 3 moles of Sb plus 3, and I realize that for every 1 mole of antimony plus 3, it was created by 1 mole of antimony. And 1 mole of antimony gives us a 121.8 grams of antimony. Sorry, the periodic table that I'm referencing only gives me to the tenths, tragically. So when I do this math, I get, with 6 eggs, I can do 1.996 grams of antimony. Okay, so that would be answering the amount of antimony. Now percentage in the ore, the percent of antimony would be the mass that we found divided by the entire mass of the ore, which was 9.62 grams from the original problem, multiplied by 100. So, and I'm bound to 366 here, and it would be 20.7% antimony in the stibnite, or the antimony ore. Okay, there's our 2 answers. So we want to balance very carefully, being sure to pick out that we are in an acidic environment, so that we can depend upon the hydrogen ion to do our balancing. Just being careful of the setup, understanding what we're given, what we need. There's our answer.